Hi, everyone. My name is Niels Bantilan. I'm the Chief ML Engineer at Union.ai. Just want to quick thank to the TMLS and MLOps World Group for inviting me here again. Yeah, super excited to share with you what we at Union and the Flyte community have been working on. And as you can see from the title of the talk, it's very much about agents and what this. Yes, great. It's always good to be skeptical. It'll be about agents and what kind of orchestration tool and orchestration requirements agents have in 2025. So before I jump in, just a brief introduction on myself. I've been in the ML AI space for more than 10 years now. Started off in data science and worked a lot sort of with survival models, statistics, and went into NLP and classification. And yeah, I remember when the Transformers paper came out. So I was sort of in this world before then. I maintain and have authored a open source package called Pandera. So that's sort of my one of my contributions to the open source. It's a data validation tool. I'm also one of the core maintainers of Flyte, which we'll be talking about today. My background is actually in biology and public health, so you know, just I like to call that out just to let folks know that there are many paths to this field if you're interested. And my mission these days is to build open source and sometimes closed source commercial tools for data and ML practitioners. Yeah, I see. I like the responses in the chat so far. It's great to sort of look at new shiny objects, and my process for this, which I won't go into today, is to sort of understand them more deeply. And typically, what happens is you see that they're kind of boring and pretty much mundane in many cases. Yeah, it's like fancier operators that we're getting access to. Okay, cool. So today's agenda is I want to go back and revisit orchestration as a word and as a term that we use here in this industry, and go into how it's being redefined by modern AI systems. I'm going to highlight 5 or 6 of the biggest challenges that are facing builders today with both AI, the fancy new shiny objects, but also just classical ML. How do you scale? How do you create quality data sets? This kind of thing. With a slight focus on the newer stuff. This is based on our learnings from the open source community in Flyte and also with our customer base at Union, which you can think of as a supercharged Flyte with a lot of fancy enterprise stuff. And I'm super excited to announce our first set of public demos, and really, it's really laying the vision and laying the foundation for Flyte 2.0, which we will be releasing in little milestone chunks, as I'll show in the very end, and kind of lay out some of our roadmap for the rest of the year and then some. Yes, feel free to ask actual questions in this Q&A section. I'm happy to pause the presentation at any moment. So if we go back to, let's say, 2012, which is roughly around the time I got into data science and ML, the focus on the tooling was around ETL. And those were the big data, if you remember that term. These were the big, hairy problems at the time. And when it came to machine learning, you know, there was deep learning, there were deep neural nets, and then there was all sorts of other models, support vector machines, random forests, things that are still like the workhorse of a lot of applications today. But model training for a lot of the cases could fit on your laptop. Like you can fit the model on your laptop, you can train pretty quickly on your laptop. And as we moved to 2014, you got microservices that became kind of a fad. You needed to orchestrate multiple microservices together. And around 2017, the whole pipeline, data pipeline, ML pipeline tooling kind of came up to the front. Then as all these tools, which started off at companies like Lyft and Uber and the FANG companies, they spun off and open sourced, and there's a community around them. Around 2020, 2021 came along the managed ML orchestration. So all these teams who spun off into their own communities started commercial offerings for the tools they were building in the open. And fast forward to today, where, as I mentioned earlier, agents are kind of all the hype today. But again, I'm not going to kind of unpack that term in this talk today. But we're going to try a bunch of stuff, right? We, as in the technology community, the AI community, the ML product community, we're going to try a bunch of things with agents. They may not work. They may be brittle in many cases, but I think this is, as someone who comes from a biology background, this is okay to me. It's okay, maybe not the environmental impacts, but I think more broadly, it's okay to try a bunch of things with a new shiny object. And this is just the way it goes. And there will be a boom and bust in this area as well, I think. So some of the context here is orchestration needs to evolve again, basically. And these are quotes pulled from various teams. The first one here is that basically with agents, you can't hard code a fixed path. And a lot of orchestration tools out there assume that a human writes a workflow or a pipeline, and things might happen in the nodes of that pipeline, but the overall shape of that pipeline is the same and kind of static. There are also a lot more different tools today that are of the like of things like MCP and A2A and all these new protocols that are cropping up, where there's even more of a tooling burden and operational burden around managing and deploying these tools. And AI orchestration is kind of emerging as one of these terms to sort of encapsulate all of these, all the tools and all the infrastructure that needs to be put together to support agents. So working with a lot of customers, many of them in classical ML land, you just get data, get labels, clean the data, train a model, you deploy it to some endpoint, or you do batch inference on them. But also we have a few who are building on top of us to build agents and agentic-like workflows. And 6 of the common pain points we hear is that it's kind of annoying and a steep hill to climb to learn a DSL, a framework to orchestrate these different components. It is, onboarding is costly. It's costly to add new functionality, and it's also difficult to debug. If you've ever worked with a orchestrator and something goes wrong, more or less you'll get maybe you'll get error messages. Maybe you'll see where exactly in the DAG things went wrong, but this is not always the case, and it's hard to reproduce errors that might have happened intermittently in the cloud somewhere. There's also limits of static execution, which I mentioned earlier, especially in agent runtime. But even with classical ML pipelines, maybe you have an out-of-memory error and you want a larger machine. How do you actually handle this in a static DAG? This is a challenge, hard to fan out. It's hard to fan out computation where you need to do kind of parallel compute across many different machines. This applies to data processing all the way to a kind of deep research agent who spawns sub-agents to do answer sub-research questions. Then you have brittle pipelines, which effectively can't tolerate failure, and you have to start from scratch when a failure does occur. You have to write a lot of glue code and a lot of kind of supporting code beyond your business logic to make your pipelines robust to failures like this. And finally, best practices are hard to implement. It's hard to manage. Versioning, how do I version all my models and artifacts? How do I coordinate deployments? How do I know which model to swap out with the production model? These are things, if you're a practitioner, you have a sense of how to implement all of these things, right? But whenever a new kind of compute paradigm, which I would argue LLMs as a tool are a new type of compute paradigm, LLMs and multimodal models, these things kind of compound, and you kind of have to build new and perhaps even somewhat familiar, return to somewhat familiar things like dynamism. So after several months of a lot of hard work from our team, we are very proud to announce the release of Flyte 2.0, which is effectively a durable, fully dynamic, resource-aware AI orchestration platform. So I'll have all sorts of links and stuff at the end if you're curious and want to check it out. But really, just to set your expectations, what we're releasing today is early beta program for developers who are interested in contributing. We're open sourcing our SDK. This is the code that I'll show you in a second. I'll show a few demos. I may not have time to get through all of them, but basically, if you're interested in getting involved in terms of shaping the platform and trying it out, you can join our beta program, and you'll get access to our private backend where you can run all the stuff that I'm about to show you. So in terms of pure Python authoring, let me quickly give you a sense of how Flyte 2 works. If you don't know Flyte 1, that's cool. You don't have to understand the sequel. You don't have to watch the previous movie. Okay. So I'm going to start off with a very simple kind of toy example. And I'm going to have Cursor kind of fill in some of the gaps here. So I'm going to square a bunch of numbers. I'm going to loop through range n. So I'm going to loop through 10 from 0 to 9. And I'm just going to square them, right? So this is Python. Y'all are probably super familiar with this. I'm just printing this on the left-hand side of my CLI. Now, to quickly onboard, we made it super easy to simply import Flyte, create a task environment. So this is now you have to think about cloud stuff, right? So you have an environment. You're asking for one CPU, and I want to get it from some cloud that I have access to. I'm going to name this environment Square. And all I'm going to do, as Cursor has already jumped ahead of me, I'm going to decorate these functions with @and.task. Right? So now, instead of just calling the function, I'm going to initialize Flyte. And we're going to say flyte.run main with 10. I'm going to square the number 0 to 9. And it's just Python, so I'm just going to run the scratch.py. And actually, oops, I ran it, and I forgot to print the URL. So I'm going to print the URL that this creates. And it's a local one. And that's fine. But Flyte kind of gets out of the way, right? So it's basically just Python. But if I initialize from a configuration, which I have over here, so that configuration file basically points to a playground environment that I'm going to demo stuff on. And I run this again. It's going to give me this URL. And fingers crossed, the demo gods are OK with my presentation today. What this is doing is it's running main in a Kubernetes pod. If you think of this as a just container in the cloud with all of my dependencies, which in this case are basically just Python and Flyte. And it's gonna run like Python, right? So it's just gonna sequentially run Square. And And we can do better than this, right? So we can actually, instead of using Python's map, we can use Flyte.map and effectively parallelize all of this. So if I run this again, it's going to start up another container in the cloud. See how well this is progressing. Okay. Yeah, my demo gods are not being generous. So I'm just going to show you a container that's already a workflow that's already run here. So this was a sequential one, right? So each square invocation ran sequentially, and here's one that ran in parallel. So with Flyte.map, you can parallelize things. The other thing we embraced about Python is that now we support async. So instead of using map or Flyte.map, because in many cases you might want concurrency, but you don't need it to be embarrassingly parallel, or you just want to use the constructs you know already. We can use async await. We can loop through and call square and gather it at the end here. All right, so if I run this again, yeah, I think we are demoing some other stuff, and our team is kind of running stuff as well. So these are running slower than expected. But you can see Flyte.map effectively parallelized all these square operations. And now this is the async await version of this, right? So why is this important? Well, we already know distributed computing is important for everything from data processing to ML to AI agents and AI model training, AI inference, batch inference. So this is just a super Pythonic way to parallelize your operations. So this is the one thing we embraced about Python. And then when we support other languages in the future, we will build them so that they are native to that language. The next pain point is around debugging. It's hard to observe state, failures, logs, and it's hard to catch and react to errors that happen at runtime. So what I'll show you next is a workflow that has a task that it's kind of a memory hog. So this may or may not produce an out-of-memory error. And in this function, I am basically going to try a bunch of memory overrides. So I'm going to try a bunch of different memory settings for this one workload. So imagine memory hogger is kind of like a training job or something like that. Well, with Flyte 2, you can catch that out-of-memory error right here and then respond to it somehow, right? You can raise the error. And actually, what Flyte will do is recover from these failures. So if I go to this advanced example and I run multi-loops, actually, I'll run this with a different setting because we have, yeah, I think we cache, yeah, so we've cached these tasks, so they succeed immediately. I'm going to give it a different input and show you what I mean. So these three have been cached, but these retry groups haven't. And as you can see, we're retrying these out-of-memory errors until they succeed. And this is something a static workflow orchestration system does not do. So actually, we found that with retry group 4, we need even more memory for this setting, right? So this gives you full observability into what happened in your system. You can look at the logs. You can see exactly what went wrong. You can see that there's an out-of-memory issue. So what I'm going to do next, since I really don't have too much more time, oops. Oh, I don't know where my presentation went. Ah, okay. Cool. I'll show you a few more examples, and then I'll kind of go into the roadmap and sort of give you what's next. This third pain point around dynamism, right, it may sound like it's very agent-centric, and I'll show you kind of like a toy agent example, but really this is super important even for many other types of workloads. But here I'm going to hop over to this fun example we call internally the peanut butter and jelly example. So in this example, this is kind of a dummy LLM plan. So this is like the execution plan for all the tool calls that an LLM would potentially come up with. And basically, it expresses all the tasks that can sort of be done in parallel. And you can imagine get bread, get peanut butter, get jelly, spread peanut butter. All of these are kind of like the agent's tools, right? And so the plan that an agent can come up with is based on kind of like this list of things that it can compute in parallel. If I just run this real quick. We'll see this kind of a placeholder prompt is make a peanut butter jelly sandwich. And that dummy plan that we saw in the editor is being carried out in sequence, but with the tool calls that can happen in parallel because they don't depend on each other, right? So first it gets the ingredients, it spreads the spreads, and it assembles the sandwich in the end. And I guess in the end, you should eat it. But this gives you a sense of like the dynamic nature of how you can kind of assemble the building blocks just using Python. And any other component, like maybe you're doing OpenAI calls or Anthropic calls, or you're hosting your own model. And you can kind of change the shape of your pipeline and your workflow dynamically. I'm just going to show you a complete run of this, but just to hammer home on the scalability of this system, I'm going to show you this distributed random forest example that I have previously run. So let's see if I can find it over here. So basically, this is a random forest where I create a data set that won't all fit in memory, right? So if I try to load all the data, it's going to give me an out-of-memory error. But what I can do is, since random forest is just an ensemble of decision trees that are trained on subsets of the data, I can partition up the data and run the partitions all in different machines. And then in the end, I combine them all back into the random forest, and then I can evaluate it. It doesn't perform very well because this is a synthetic data set. But you can see that I've parallelized all of these operations, these training runs, and they started at the same time and completed at roughly the same time. The last demo I'll show you is this question around brittle pipelines. If you've ever worked with LangChain, if you've ever worked with any of these frameworks, they typically, like without any more work, they run on a single Python VM, right? You pip install LangChain, you write your code, you might containerize that whole application, and then you ship it off, and then it runs, right? Add a lot of logging, you do a bunch of stuff. But what if I need to do a tool call across kind of instance boundaries or container boundaries? Maybe I want to do a tool call to a code sandbox where I can securely run code, or run a tool of a trusted function that I implemented myself that I need, for whatever reason, want to run on a different container. So I'm not going to show you what I just described, but I will show you how easy it is for Flyte to recover from failures. So I have this crash recovery example. And as I run this, I'll kind of talk you through what exactly is kind of happening under the hood. So in this code, I'm just iterating through a range of n numbers, and I'm intentionally failing at index 2 here, right? And this is just a sequential for loop. And as you can see, do work, the first call worked, the second call worked, but at index 2, which is the third call, there's a little gap here. And this was basically the error that I synthetically raised in this line of code. Yet the pipeline still finished, and the pipeline still continued. And this is because we have, our own, we implemented a proprietary logging history system where you can basically replay immediately from any failure and then pick up from where you left off. So this is our take on both dynamic pipelines, but also resilient and fault-tolerant pipelines. And then this last part, really, with best practices, we do automatic versioning. Everything is versioned. We have built-in multi-tenancy, so these would be typically your dev stage prod environment, and they are all isolated in terms of the nodes they have available to them. And as you saw in the code, we have declarative on-demand infrastructure. So if I wanted to say, request a GPU, I would ask for a GPU over here, and I'd say, hey, I want an 80 gig A100. And that's pretty much all you have to do to request for one from a user perspective. Okay, so kind of one of the takeaways is Flyte 2.0 is a fully fledged, fully functional agent runtime. But it is not only that. It is also a dynamic, fault-tolerant, scalable, infrastructure as code, AI ML orchestrator. So you can build all of your ETL, build all of your model training and evaluation, and as well as your agentic workflows all on the same platform. Because really what an agent is you have an agent router and it takes some input and it makes a decision. It's basically an if-else statement, right? So that's one kind of like operation you can do with an LLM. It's just much fancier. So real quick, our roadmap is today. We're opening up our private beta. So there'll be links in the next slide on how to join this. We're open sourcing our SDK for local execution. But if you join our private beta, you'll get access to the cloud, the UI that I just showed you. We'll be showing API docs and examples. And sort of through the course of this year, we're not committing to specific dates here. But roughly speaking, for the rest of the year and then some, we'll be releasing our full Rust core. So as you can see, everything pretty much ran very quickly, and Rust was one of the reasons behind that. We'll be opening up our plugins for distributed training, things like this. And milestone 3, you'll get access to a local sandbox, so you can access the UI and the backend kind of in a little mini Kubernetes cluster on your laptop. Milestone 4 is our open source beta, and in 5, you'll be able to, it'll be fully GA, so you can install the entire platform on your organization's system. So be that AWS, Azure, or GCP. So these are the main points. It's really, we've built something for end-to-end AI orchestration to really bridge the experimentation and research to production gap. We've really optimized the engine. We're building out real-time inference and observability capabilities as well. Yeah, we have all sorts of nice enterprise security features on the Union.ai side. And so, yeah, you can reach out to me. You can join our private beta, and I can, if you're interested, we can hook you up. And I will end here for answering the questions here. So, sorry, I'll go a little bit over time if folks don't mind, but Anonymous asks, how does Flyte 2 balance flexibility with guardrails so agents don't go rogue in production? This is something we don't have a opinion on, really. Like, obviously, our opinion is yes, add guardrails, but we haven't built a framework here. We've built a runtime for you to build all of the guardrails in a flexible manner yourself. This is one of the things we learned. The more, it's kind of parallel to the bidder lesson in that on the infrastructure and orchestration side, the more assumptions you build into how you expect users to write these things, the more pigeonholed you get into a particular era of AI and ML, right? So in Flyte 1, we built a bunch of assumptions, many of which that have stood the test of time, but dynamism wasn't one of them. So in Flyte 1, everything was statically compiled, graphs and DAGs. In Flyte 2, by default, everything is dynamic, and you can opt into the statically compiled stuff if you really like that mode of programming. So in terms of guardrails, you build that in yourself, right? So that's what I'd say to that. You mentioned that Flyte now supports Pythonic async functions. How does Flyte capture the state of an async workflow so you can resume it reliably after a pod crash or network failure? So this is what I mentioned around our logging system. So we basically have a specialized logging system that is able to record what has successfully run already. So in the case of a network failure, all successful things that have run don't have to rerun. And so you can think of it as a log cache system that allows you to recover from pod crashes or network failures. You describe Flyte 2 as a resource-aware orchestrator in practice. How does it track and allocate compute or GPU resources for AI workloads? So that's exactly sort of what I had shown you here with the resource requests. So here, we directly just ask through the declaration of this task environment resource request what exactly you need for a particular workload. And in the multi-loops example, or actually in another example I didn't show, you can override this, right? So if I have a task called Umer that I know will out of memory, I can call it with overrided resources such that I have more memory or I have a different instance, things like this. What is debugging like in Flyte? You mentioned debugging literal pipelines. So our story for this is that everything can run locally. So as I showed you before in this Scratch example, if I just init, everything here just runs like native Python. So that means I can, assuming that you can run, that your laptop has enough hardware and enough juice to run the workload, you can run things locally, debug things locally. And that means also unit testing your entire pipeline very, very easily using things like PyTest. I don't think it works yet, but we will have a debug button. So maybe I can find something here. OK. So what we're going to be launching very soon is a button. Just imagine a button here that says debug. And if you click on it, you get a VS Code editor running on the pod that basically allows you to reproduce exactly the production conditions that produce your error, assuming that it's some kind of user error, right? For intermittent random errors, if you're trying to do a network call to some external service, maybe it's very hard to reproduce. But for things like out-of-memory errors, user-related issues that have to do with a funky combination of your code and the hardware that you're using in the cloud, then the debug button will kind of be a godsend, because you can't do this, you can't pull the code down locally and try to run it. OK, so we're 5 minutes over time. Thank you so much for sticking around. And let me just say, follow me on LinkedIn. I'm always available there. You can follow Union.ai as well, and you can join our Slack community. But if you really are curious about Flyte 2, go visit these 2 links. The first one is to join our private beta. The second one is to check out our SDK and docs. And with that, I will end the presentation. Thank you again so much. See you later.